I'd like to blame him for the reason that I'm in the AM space. So John's actually the one that introduced me to the team at 6K, and what ultimately resulted in us merging the entities to form 6K Additive. So he's the guy to blame.
Hello and welcome to Critical Material Production with Plasma, a podcast and video miniseries from MANSUS and 6K. This is the second of 3 episodes in which I talk with Frank Roberts, who is the president of 6K Additive, and John Barnes, who, amongst very many other things, is the founder and CEO of Metal Powder Works. Hopefully you've listened to the first episode in this mini-series, which is all about plasma and how that is harnessed in 6K's UniMelt platform. If you haven't, I would suggest that you do, because it will give you a good grounding on their technology and enable you to follow along better with this conversation and subsequent conversations. Collaboration is often touted as the key to unlocking the potential of AM, and both 6K Additive and Metal Powder Works do produce metal powders, but do so in very different ways. By working together, they've been able to tackle some materials development challenges that would have been impossible if they'd have done so alone. Both processes bring significant sustainability benefits to powder production for additive manufacturing. As we hear in this episode, the choice of materials available for metal AM is a fraction of that available for other processes. And if AM is going to deliver on its long-touted promise, we're going to need a revolution in the way that the materials are made. Beyond additive manufacturing's significant challenges in materials availability, we hear in this episode why there's a reason to be generally optimistic about metal additive manufacturing and why Pittsburgh is the perfect place for producing powder. I started off by asking Frank and John how they ended up working in this niche within a niche, producing metal powders for additive manufacturing.
My name's John Barnes. I'm the CEO and founder of Metal Powder Works. I'm also the president of Barnes Global Advisors and an adjunct professor at Carnegie Mellon and RMIT University. We founded Metal Powder Works a little over 5 years ago, and it's a completely different way of making powder. The hallmarks of our process are that we convert a solid wrought bar, into powder through a mechanical means. There's no melting, and because it's a solid state process and a mechanical process, we get very consistent output from the process. So our notional powder size distribution is 30 microns, but more importantly, we can basically choose that. We can dial it in. So we have control over the size and the shape. And so we get a very high yield process because of all of that, and the fact that we're not using industrial gases. We have a very sustainable process. And the thing that we like to point out to your kind of where you started this question was, currently there's 16 approved AMS specifications for metal powders. There's over 2,000 approved AMS specifications for bar stock.
A ways to go. So how did you end up launching Metal Powder Works? You didn't just suddenly wake up one day and think, okay, I'm going to get into AM.
Yeah, that's a good question. So my partner, Chris Aldridge, and I, we first started working together at Lockheed Martin Skunk Works, and we were involved in a lot of different forms of additive manufacturing. I've been fortunate to get started in metal additive manufacturing in the late 90s, and as a materials engineer, I was always interested in the process, but also the feedstock. And Chris left Lockheed to go do some other things, and then I went on my own journey, went to Australia, worked for the National Science Agency there, where we did a lot of powder work, stood up their additive manufacturing innovation facility, Lab 22. And when I came back to a company that was doing titanium production, but had made an investment in a service bureau, so I kind of oversaw that and qualified the first parts for Airbus on a series production aircraft. Chris came back to work in that facility down in Austin, Texas, and it was kind of at that point where the variability in the powder and the sources of powder, it could be the same alloy, but when it's made by a slightly different atomization process, the characteristic of the powder is different. Therefore, you have to twist the knobs and dials on the printer to get it to behave differently, which runs afoul of doing things for aerospace where they don't want you to be doing that. You have a fixed process. And we just said, honestly, there has to be a better way. He was kind of at the face of it with the machines. I'm looking at the process economics of it, and I know how much it costs to make titanium. I don't understand why Ti-64 powder costs what it does. But then you go look at the economics. If you have 40% yield, it becomes expensive. And so that's a little bit where we started from, which was, boy, there's got to be a better way. We literally started with a clean sheet of paper independently. We both worked on it. I love a good spreadsheet, so I cracked open Excel and ran the math and said these are the things that have to be true about a process. Chris came up with something very, very similar, and that's when I thought, well, we must be onto something if the math is working for both of us. And then, as any good story goes, Chris lives in Texas, so he's got a shed. We literally started this process in Chris's shed. So we did a little experiment there. We kept going on, trying to do a little 10x improvements every time. Then ultimately we needed to move to the super shed, as we affectionately called it, which was a no kidding building with air conditioning and everything else. So that's really where we started. We just wanted to solve a problem around consistency.
How about yourself, Frank? Where's your journey taking you up until now?
Yeah, so I'm unlike John. I only have one title, president of 6K Additive. He's carrying many cards. So got into been in specialty metals my entire career. Started with ATI, and then ultimately went to small business that I eventually acquired, and decided to embark on a journey into the world of making powders for AM. We do it a different way. You would have heard in the previous podcast about all about 6K's plasma technology. So the 6K additive group, we're leveraging that plasma to spheridize particulate instead of atomize. So as John just mentioned, the yield proposition of traditional atomization is a process that I would say largely uncontrollable in terms of particle size distribution. And so, what we're doing is we're creating an angular feedstock in a very efficient, controlled manner ahead of time. That is the right elemental chemistry, and it's the right volume of particulate. It's just the wrong shape, and then we're injecting it into the plasma to spheridize. The similar kind of story as MPW, about 90% less energy needed and less carbon CO2 created in producing our particulate. And we focus really kind of in the same area that John does. It's all about powder consistency, so that a lot today is the same as a lot tomorrow, as a lot a year from now. And so our view is that consistency leads to less turning of the knobs in the printer, and so they can be much more dependent on just a constant very repeatable powder input feedstock to their process. So kind of a lot of synergies in terms of the product we're producing with MPW, but a very different approach in terms of how we produce it.
Yes, well, obviously we've already heard about the UniMelt and the plasma system. So, John, in terms of direct powder, what are the fundamentals of that technology? How does it actually go about creating the powder?
Yeah, in its simplest form, we take a round bar and we're rotating it at a couple thousand RPMs, and then our proprietary tool runs along the length of the bar, and that has to use a patent term, a plurality of teeth, which is one of my favorite words. And we contact the bar at a frequency, and currently when we do that with the current length tool that we have, we generate 4 million particles per second. So the dynamics of this process are very high, and as a result, those particles get whisked away from the bar immediately and captured into its own system, and it's solid state, so you can basically watch it happen on or at least on the receiving end. You can't see something moving at that frequency.
And the powder that you're creating is not spheroidized. It's an angular.
The optionality piece to me is kind of what's interesting for people who really do need to have super round particles. Frank's got that process. For people who don't need super round particles, maybe our process works well enough. And there's an advantage to doing that sometimes too, which is, when we've run our copper powder in a powder bed process, the laser coupling is 90%. If you do it with conventional round shiny particles, it's 10%. So that's a consideration that needs to be taken into account. It's unique to copper. It's not true for things like titanium or steel or other materials. It's those very highly reflective materials.
So that brings us on nicely to the MOU that you two signed, or your two organisations signed, specifically around copper and copper alloys. Obviously, that is one of the materials that you see, especially on the trade show floor, because I mean, AM parts out of copper just look nice. When you're used to that sea of grey, then you see something built in copper, and it just it works for trade shows. How did you come together for this, and what are you each bringing, I guess, to solve those challenges around copper specifically?
I think we've been talking about it for a while, years. So John and I've had a lot of conversations about how we work together. Did some really early demonstration work. I would say at the start of Metal Powder Works, and just proving. I think the first trial we did was an aluminum alloy, just kind of seeing how the two technologies couple. And so we've continued the conversation. It only makes sense. John and I go back before I got in. Actually, I like to blame him for the reason that I'm in the AM space. So John's actually the one that introduced me to the team at 6K, and what ultimately resulted in us merging the entities to form 6K Additive. So he's the guy to blame. But
No dignity goes unpunished.
yeah. So we've been talking a while, and we as we really started over the last year and a half, growing our market share, and really scaling our technology. The demand for copper continues to increase. It was something that we didn't have necessarily a solution for, kind of ready made, and so the conversation with John and the team at MPW's, I think, got a little deeper, and it's just a perfect fit, because he can essentially create us a much more efficient feedstock than any other technology. So it's this is our customer base is looking for the to use John's technical term, very round particles, and so we can check that box with John's feedstock pretty easily. So it just makes a ton of sense for the two entities to join up here.
Yeah, and I think when you when you think about copper specifically, where ultimately you're interested in conductivity, it's that for a designer, you've got the tolerance stack up issue. In copper, you've got a defect stack up issue, and so chemical purity is one. Oxygen, which copper loves oxygen, but oxygen is the enemy of conductivity. And then so also having so any chemical impurity that's going to be in there, any oxygen that's going to get in there, and any defects that you create, pores or whatever, is going to defeat the conductivity piece of it. So that's I think one of the things I'd like to think anyway that attracted Frank to the process, because we're going from a wrought bar, which you can control the chemistry very, very well. Secondly, we don't introduce defects in the form of, sometimes with atomization, you can inject, the gas gets entrapped inside of it. It typically doesn't escape during the printing process because it's so small. But it's a defect that will hurt the conductivity overall. So with the combination of our processes, we were able to show that we actually improve the chemistry. His process, the UniMelt process, can reduce the oxygen, anything that's in there. And so in some ways you can think about it that we start with a slightly more easy to get bar. It's not a super expensive high chemistry, and we're using the process to get to the chemistry that we want. And so we both have very consistent processes. We can generate a population of powder that he can convert into spheres of a very controlled size. So and in some ways you could think about the combination of the processes makes a perfect atomizer, except we're not atomizing by the true sense of the word.
what's next then? What have you learned from this project or studying copper? How could that be applied to different metals and alloys, do you think, in the future? Because like you say, we're an order of magnitude behind other processes in what metal AM is able to offer. So what's next? What's the next lowest hanging fruit, I guess?
Well, we got a list, don't we, John?
We do.
And how low is the fruit hanging?
There's definitely some
Yeah,
low-hanging fruit for sure.
I think that's right. Yeah. I always tell people, we're not here to poke at atomization. It's a decent process, and it has created an industry that's, depending upon who you believe, something on the order of $14 billion, but 95% of it's water atomization. So additive doesn't believe it can use that. The rest, we need some sort of change if additive manufacturing is going to succeed, because we're kind of at a supply and demand are at parity. So that drives certain behaviors. So I think fundamentally, where 6K and Metal Powder Works is in a good space, because we're actually solving a fundamental economic problem, which is that macroeconomic case of supply and demand. There's nothing. Nobody ever said that every metal should be atomized to get to a powder form. It's just that atomization has been the predominant path to do that. But it's centuries old. It's how we used to make shot it still is. And, it's how we used to make shot for things. So they have these shot towers all over the world. It's just pouring molten lead into a large, a tall building and letting it form spheres on the way down as it cools. So this is not a new process. Modern day atomization is about 90 years old. We've squeezed all of the efficiency that we're likely to get out of it. So I just view this as, there are a host of other materials. They have issues with availability. There's technical issues around segregation and other unique material sciencey things. Our process, our combined processes, take it in a slightly different direction. We just have a different view. So some materials are going to be super easy for this process that would be hard for atomization. And that's, I think, ultimately where we want to be.
What are the characteristics that would make a material particularly difficult for traditional gas plasma atomization and lend itself more to either one of your processes or a combination of your processes?
If you can get it in bar form, it probably makes a lot of sense. If it's easily machinable, that's the second box that really needs to be checked, for John's process to work. So I think beyond that, then you get into some of the, when you think about some of the higher temperature materials that are out there, and some unique alloys that are being worked with today for hypersonic applications, things like that, where you can easily source this material in a bar form. Not quite as easy to atomize, I would say, efficiently. The yield is going to be a big problem, because the cost, just the sheer cost of some of these materials can be astronomical. So when you're losing, 50%, 60% to offsize, that's not going to enable market growth. That's going to hinder it. And so this is where these are the areas that John and I are talking about. How do we work together? Kind of what's next for us. So as we scale copper and we start to look at some of the other the next steps, it's those places that atomization and just the sheer cost and efficiency they're not going to make sense.
Yeah, so I guess a traditional atomization plant, as it probably would be, is going to cost quite a lot of money, and I'm guessing it's rigged for scale, as in it can produce a lot. Okay, it's going to produce it with a wide PSD, so depending on your application you might not get a lot, you might get enough. But I understand that between your two organisations, that the scale that is relevant to AM is your natural area at the moment, or you can scale up, but we're not talking hundreds of thousands of kilos of any one alloy at the moment, are we? What's the kind of scale that we are really looking at for AM?
Yeah, that's actually a good point, scale. So, so as much as if you're in the additive manufacturing industry, you think it's enormous and everybody's doing it, but it's still less than 1% of global manufacturing. So it's not the powder market is not tremendously large, which favors very efficient processes. So to Frank's earlier point, there's nuances to all of these processes. Plasma atomization requires a wire. Well, not everything can be processed into a wire, and typically wire is the result of making an ingot, turning it into bar, and then turning it into wire. So will be limitations around that, and if the powder market, it's hard to say what the consensus estimate is, but let's say it's less than $1 billion market today just for additive. The materials that are specifically susceptible are the materials like Ti-6-4, which don't have a powder metallurgy market to rely on, where the oversized powders can be sold. If you look at materials like some of the superalloys, it's okay. It's a good material to process in atomization because there's a market for all of the different sizes. We don't need to be there. That's at least as Metal Powder Works. Where we bring efficiency to the market is everywhere else, is everywhere where maybe additive is the only market for that powder, and it's going to be cost prohibitive to do it with atomization because of the yield. That's fundamentally untrue with either one of our processes, and together they create that sort of perfect atomizer. You can have the shape that you want, you can have the size that you want. And then pushes it on people, which is, what is the size and shape that you want? I don't know. I never had that option before. It was always, whatever you gave me.
That's a really good point, John. I think about often you talk about the size, the shape, that customers want, and you talked earlier about spec, and that's the tunability of these processes, the flexibility, and the repeatability. Most times they don't know what they want because they know what they've been able to get, and they've tuned a process to get there. Some of the things that we work with customers on efficiency and just their productivity, and this is one of the things that excites me about coupling John, the MPW and 6K together, is that consistency allows them to maybe tune their process a little bit further. And now you're seeing it's not just about yield and lowering overall cost, just of the raw material. It's the efficiency of their machine and how that repeatability, and they can become more productive in their printing process and lower overall part cost, and then that leads to broader market adoption. So I think this is like 1 + 1 = 7, really, in the grand scheme of things.
And I think that Frank brings up a different point, which is we both come from a background of I'll say manufacturing and things where specs are kind of important. And I believe having observed and been in additive manufacturing for a while, it's going through a transition period where I will sort of lovingly say we've looked to the printer manufacturer as the source of all goodness. And it's just to make a point, it's not necessarily true, but they have carried the weight of the industry. I think that's fair to say. And now we're seeing a transition. It's the part manufacturers who are going to be the drivers of innovation going forward. And they're more interested in specifications. And I understand that, having the best performance isn't as important as having predictable performance. Mm-hmm. And consistency, again, is key. So I'm still wildly optimistic about additive manufacturing. I think that there's a fair amount of pessimism out there, about the industry because of this and that. But I certainly see there's going to be more consolidation, but that's healthy. We look at the automotive industry. We've probably started with 100 different automotive manufacturers. We've dwindled down to a few. But if we didn't have the 100, we wouldn't be where we are now. So everybody had different ideas, and all of those ideas have to come together, and a lot of times it takes 3 of them to come together to make one good one.
Mm-hmm. It just in terms of kind of related, I guess, to efficiency. One of the one of the key selling points, and whether this is entirely genuine or not, but one of the key selling points for AM is always the sustainability angle. And although the mantra of, oh, well, it's more efficient because you're only using the material that you need, stacks up to some degree. But like you say, John, if you need to go through 3 or 4 processes to get a wire to be able to plasma atomize it, to throw 70% of it away because nobody needs it, it doesn't start to look so rosy. So how do you have any sort of either an inkling or some data that shows how your processes stack up against atomization, traditional atomization, kind of on a sustainability front?
Outside of the MPW raw materials, it's mostly scrap based. So it's coming from some revert stream, either subtractive or additive revert stream. So you're kind of always starting from scrap. What really drove us to dig deeper and explore the opportunity with MPW was the fact that they could create a unique feedstock that was so sustainable. And so you're just not going to get that anywhere else. So for us, copper was a feedstock that we didn't really have a path for creating, an angular feedstock in a way that we considered sustainable. And MPW was just the perfect fit for that. So, starting from scrap, usually with everything else, copper was a unique one, and John and I are starting to identify kind of the what's next, and where it makes sense, and kind of where the industry, I would say, largely struggles to produce a sustainable low cost solution to some of these new alloys that are under development.
Okay. In terms of, I guess, like the financing in this and the money side, how does the old compare with the new in that regard? So in terms of setting up an atomization plant versus maybe using one of your technologies or your technologies combined.
It's a good question. I don't think we talk about it enough. I know at least at 6K Additive we don't. We are always anytime we meet with an investor, we always talk about the technical capabilities of the system and how unique it is and how efficient it can be. But we don't really talk enough about how it compares to traditional technology. So I think this is another area that two very different approaches to making powder, but very similar in terms of its flexibility and efficiency in terms of capital required for sizable, for scaling the operations. If you were to compare, if you wanted to put in a plant that I would say would be as flexible as a MPW 6K additive, in terms of alloy capability, you'd need maybe 3, 4, 5 different types of atomizers, to cover very different melting points, from aluminum being more at the bottom all the way up to some of these refractory metals, and John, you might have a better idea than I do, but a tremendous amount of money for each one of those atomizers. Where this is really unique, both technologies really don't care as much in terms of the capital deployed about the alloy you're producing. It's more about the setup of the machine. And so it's an important point, in that not only is it an efficient process in terms of the product we're creating and the energy needed to create that product, but it's a very efficient use of capital to achieve the scale required to keep up with the growing industry.
Yeah, totally agree. If additive's going to succeed and move in to have 100 different, powder options, you're talking about massive investment in atomization if that's the only answer. Whereas the processes, for us, I know we can transition from, one material to another because our production generator is separate from our collection system, so we can roll in a new collection system and pretty quickly be generating a new material without fear of contamination. That's really hard to do on the atomization side.
Nice. Okay. Well, our not eagle-eared. I don't know what the equivalent of eagle-eyed is, but for having good hearing, our eagle-eared audience may have noticed that. Yeah, I have a non-American accent. That's because I'm from the UK, just south of Manchester, the world's first, some may say greatest industrial city. You guys are not that far away from each other in Pittsburgh, so I'd just like to know why Pittsburgh? What's special about Pittsburgh that's brought you both there, and how do you see kind of the ecosystem around you developing in future?
Well, maybe since I'm not from Pittsburgh originally, and my family's from Pennsylvania, although the Barneses are from just north of Manchester, so back in the day. Um, yeah, so growing up in Atlanta, it's not a manufacturing town, and so moved to Pittsburgh about 8 or 9 years ago, and just kind of both my wife and I sort of fell in love with it, but it was this you had an image in your head, and it was a little bit different than that. It was a lot greener than we expected it to be. But when I started looking for engineers and looking for people to work in facilities, it was like, yeah, this is what we want to do. So this is an area known for strategic materials. I like to say that 100 years ago it was about access to the natural resource was coal and iron ore. Today the natural resource is people who've been left from centuries of doing materials and manufacturing work. So this area likes manufacturing. It's good at it. There's a lot of unique capability in this area. It's why we relocated Metal Powder Works to Pittsburgh from Austin. 40% of North America's powders come out of Pennsylvania. So there's a good workforce that understands powders here. I know, Frank has benefited greatly. He's gotten some great engineers from some of the other powder companies, as have we. So that evolution of the workforce, I think, is a big deal. The culture in Pittsburgh is hard to beat for manufacturing. So I view Pittsburgh as it's going to punch above its weight, or continue to punch above its weight, I guess I would say, because it's a decent place to live. It's an affordable place to live, and the workforce here is really good. So we are only 15 minutes apart ish,
Yeah.
and so that was another thing that makes total sense as Frank talks about the Coopetition piece of it. I think in Pittsburgh, the one thing I realized was that almost everybody knows everybody in Pittsburgh, and they're willing to help each other out because I think for years nobody else was willing to help Pittsburgh out. So they just figured that, well, if we don't do it, nobody else is going to. So there's a very much a spirit here of let's just get it done. Here we're located at Neighborhood 91, and we make stuff for our neighbors on our little 3D printer if that's what it takes, and they'll do stuff for us. And it's a little bit behind the nature that we wanted to, or the culture that we wanted to instill in Neighborhood 91. That neighbors do stuff for themselves. The idea that you don't have to own a truck if your neighbor owns a truck. Kind of take it to the nth degree with that.
So I'm a little different. I'm born and bred in Pittsburgh. My father was in the steel industry. My grandfather was in the steel industry. So metals is what we know as a family, and it's I'll say the subject of many a dinner conversation, talking about metals and manufacturing. So it's what we know. Like John, I agree. I think when you look at the Pittsburgh area, the manufacturing is just who we are, and the sense of community is pretty strong here. I travel the world and see a lot of places with a lot of beautiful scenery, but it's really hard to replace the people and the sense of community you have in the Pittsburgh area and how people work together. And we talk coopetition a lot at 6K Additive. The term, to use Bruce Bradshaw's phrase, we use it often. There's John started a powder company. We've been friends for many years, and he was starting a powder company. And my first thought was not, oh boy, here's competition, coming in. It was, how do we work together and grow the entities and help grow the industry. And so that's a lot of really good people from the area, all hardwired the same way. So you're not looking at a community full of service, that just wants to put service industry in. You're looking at people that are hardwired to make stuff and get things done. And so Pittsburgh's really great for that.
Good stuff. I like it. Nice town. I've been a few times now. A lot of good bridges.
A lot of good bridges.
In fact, you can't really see, but up there is it's very brown and old and brittle SLA bridge, I think, from I think it was Rapid when it was in Pittsburgh, maybe 2014.
Yep.
So it's very fragile. Can't let the kids touch it anymore, but that's one of my 3D printed keepsakes.
Nice.
Gents, thank you very much for your time today. Much appreciated it. We'll keep in touch.
Sounds good.
I'll speak soon.
It's been great.
Yeah,
thank you very much.
Thank you very much.
Take care.
Cheers, guys. Thank you again to Frank and John for their time. Thank you for listening or watching along with us. Stay tuned to the MANSUS podcast channels or our YouTube channels for the next and final instalment of this MANSUS and 6K miniseries for critical material production with plasma.